Well, here it is, folks, the final topic of the course. Oh, yeah. Remember, we started off with the scientific method and measurements, sig figs. It's been a while since we've done sig figs. How to do algebra, calorimetry, MC delta T. Remember half-life? My cat that had that pituitary, I had the pituitary tumor. She had the thyroid tumor. How to do electron configuration, intermolecular attractive forces, the mole map, rate of reaction, and wow, freezing point depression and making batteries. These videos still haven't even finished processing yet, which is weird. I don't know why this one hasn't finished processing. I'll have to look at it in a minute. But this final topic that we're going to do today is called organic families and reactions. Let's do this. Now, to understand this, you have to understand something called functional group position. There are many places on a molecule where we might place a functional group, which is an atom or group of atoms that makes the molecule a part of a particular family of organic compounds. If the group is bonded to an end carbon, a carbon that's only directly bonded to one other carbon, we call this a primary functional group. So, for example, this is a primary carbon, this is a primary carbon, and this is a primary carbon, because only one of the carbon's bonds is being used to bond to another carbon. A group that's attached to the middle carbon, or a carbon that's using two of its bonds to attach to other carbons, is called a secondary carbon. So Y would be bonded to a secondary carbon. Oh, and this would also be a secondary carbon. But this wouldn't. This carbon is using three of its bonds to attach to other carbons. Therefore, that carbon is called a tertiary carbon. Now, the functional groups we're going to be dealing with today, they'll actually share the same group of atoms. For example, maybe just a double bonded oxygen. But whether that double bonded oxygen is on a primary carbon or a secondary carbon will make the difference between what kind of family that molecule belongs to. So here's what we're talking about. First, we're going to take a look at the first kinds of organic compounds, the first isomers, the ones that involve oxygen, single bonded. These two are called alcohols and ethers. In alcohols, the oxygen is bonded to the outside of the molecule. In an ether, that oxygen is bonded in between two carbons. So outside the molecule, inside the molecule. And that subtle difference makes their properties rather different. So here you can see the isomers 1-propanol that has 3 carbons with the OH. And here you see methyl ethyl ether that has 3 carbons and the O in the middle of the molecule. 1 carbon, 2 carbon, 3 carbons, 1 carbon, 2 carbon, 3 carbons. 3 plus 2 is 5, plus 2 is 7, plus 1 is 8 hydrogens. 3 plus 2 is 5, plus 3 is 8 hydrogens here as well. 1 oxygen, 1 oxygen. That makes alcohols and ethers isomers of each other. Alcohols contain the OH group, which is called a hydroxyl group. Now, this is not to be confused with the hydroxide ion. Alcohols are not bases. When you dissolve alcohols in water, the OH does not ionize. So if you test the pH of an alcohol, it'll be 7. Alcohols do not conduct electricity. That OH does not come off. NaOH, a metal hydroxide, that's a base. But alcohols are not bases. In an alcohol, the OH could be bonded to a primary, secondary, or tertiary carbon. It doesn't matter. In ethers, the oxygen is in between 2 carbons. And it's not technically secondary, but I just put it there to say that it's in the middle of the molecule. The oxygen is in between 2 hydrocarbon chains. And the naming is based on what those chains are. In alcohols, we name it for the chain. This is 1, 2, 3 propane, And since it's an alcohol, it gets the ending OL. And because the OH is bonded to the end carbon, we call it 1-propanol. If the OH was bonded to the middle carbon, we'd call it 2-propanol. The ether is named for what's on ether side of the oxygen. And since we have one carbon on one side, that's methyl, and two carbons on the other side, that's ethyl, this is called methyl-ethyl ether. So let's look at some specific examples. Methanol would have one carbon. Methanol is the solvent that's found in antifreeze for windshield, and it's really good. This windshield washer fluid not only acts as antifreeze, but it also is really great at cleaning bug guts off your windshield. Ethanol, which has two carbons, well, that's what you'll find in wine or beer or liquor, and you'll also find it in E85 flex fuel gasoline. Very flammable stuff. And then there's 1-propanol, which contains an OH bonded to the end carbon, and 2-propanol, which has the OH bonded to the second carbon in. 2-propanol is known as isopropyl alcohol or rubbing alcohol. And 2-butanol, where you have 4 carbons, that's where the but comes from. Single bonds between them, that's where the an comes from. OL is the fact that it's an alcohol. 2-butanol says that the OH is bonded 2 carbons in from the end. By the way, it would have the same name if the OH was bonded here, here, or here. It would still be 2-butanol. Here's how you make ethanol, through a process called fermentation. Fermentation is the digestion of sugar by yeast enzyme, zymase. See, we like sugar, but yeast also likes sugar. Except when we consume sugar, we produce carbon dioxide and water vapor because we are aerobic creatures. But yeast is anaerobic, so it doesn't process the sugar the same way. When yeast digests sugar, notice it's not C6H12O6 plus O2. It's not respiration. It's fermentation. And alcohol is a byproduct of this fermentation. So we take a source of sugar, fruit, honey, beets, potatoes, any source of sugar, and feed it to yeast. And these are little yeast critters. The yeast digests the sugar anaerobically and excretes ethanol and breathes out CO2. You can actually see the carbon dioxide foaming up this mash as it undergoes, and the CO2 is actually being trapped in this tube. When the concentration of ethanol reaches 14%, the ethanol becomes so toxic that the yeast dies. So if you want to get higher concentrations of ethanol, you have to undergo distillation because water boils at 100 degrees, but ethanol only boils at 79. So when you heat it up, the ethanol will boil off first. Although water does evaporate at all temperatures, so you're never going to get pure ethanol out of this process of distillation. However, every time you distill, you're going to increase your concentration of ethanol. So if you get a good triple distilled Kentucky bourbon, that means that that's gone through the process of distillation 3 times to increase the concentration of ethanol. This right here is a copper still antique. You basically place your mash right in here, and then you add heat to it. The ethanol boils off, and it condenses in this pipe, and the liquid ethanol drips down into this pan. The highest concentration of alcohol that you can get is about 97% through distillation. Everclear, this 95% alcohol, is better used as a solvent than it is for drinking anything. I mean, you could actually, the Mythbusters actually ran a car off this stuff. They put it in a car, and the car ran and ran smoothly. Some more alcohols would include dihydroxy alcohols, which contain 2 OHs. Ethylene glycol, which you may remember is used as antifreeze, is one of them. This is ethylene glycol. It consists of 2 carbons, 2 OH groups, 2 alcohol groups. Now, ethylene glycol is not the standard name of this stuff, so let's get the standard name. First of all, it has two carbons, eth. They're bonded with a single bond, ethan. There are two OH groups, diol, and they're on the first and second carbons, 1,2-ethanediol. That is the standard name for antifreeze. And there's also, oh yeah, look at that. Woo. Yeah, you see this on the ground, you clean it up immediately, because remember, this stuff is very, very poisonous. Trihydroxyalcohols. These will contain 3 OH groups. Glycerol is a prime example of this, and we'll take a look at glycerol in more detail later because it's a product of making soap. Glycerol is not the standard name for it. There are 3 carbons, prop, they're single bonded, an. There are 3 OHs, triol, and they're on the first, second, and third carbons. 1, 2, 3, propan triol would be the name of that trihydroxy alcohol. I'll explain what that means in a little while. Okay, ether. Ethers contain an oxygen, but it's not on the outside of the molecule, it's jammed between 2 carbons. For example, dimethyl ether has an oxygen with a methyl on either side of it. See, here's a methyl, here's a methyl. We have methyls dingly-dangling off of the oxygen. Here we have methyl ethyl ether, a single carbon on one side and 2 carbons on the other side. Methyl ethyl ether. Diethyl ether would have 2 carbon chains on either side of the oxygen. Diethyl ether, by the way, used to be used as anesthetic, and it's still used to knock out fruit flies when doing genetics experiments. Don't use it on humans. We used to use it on humans. Here you can see the soaked rag over the patient's face. Yes, this would knock you out for surgery, but you stood a reasonable chance of never waking up again. So, yeah, today's anesthesiologists, they use more measured approaches. Methylpropyl ether will have a single carbon on one side, meth, and 3 carbons on the other, prop. Methylpropyl ether. Second type of isomers are those that involve double bonded oxygens. This is called a carbonyl group. Aldehydes have a double bonded oxygen on the end of the molecule in the primary position. Ketones have the double bonded oxygen in the middle of the molecule in the secondary position. And this will actually make a difference in their properties. Aldehydes are more polar. Ketones are more nonpolar. So aldehydes contain a carbonyl group on the end, and ketones contain a carbonyl group in the middle. Not between the carbons, but on a secondary carbon. So let's look at some aldehydes. We have methanal, which also goes by the name formaldehyde. This wonderful aldehyde is used for preserving organic remains, although it is extremely toxic, so they have come up with some alcohol-based substitutes. Formaldehyde can also be used in the glue that binds wood together to make plywood or particle board or oriented strand board. You don't want to burn it and cook a campfire over it, I'll tell you that right now. Ethanol would have 2 carbons. Propanol would have 3. Butanol would have 4. And in every case, the double bonded oxygen is on the end carbon in the primary position. Those are aldehydes. Ketones, methanone, would not be possible. In order to have a secondary ketone, in order to have a secondary carbon, the carbon has to be using 2 of its bonds to bond to other carbons, which means methanone and ethanone would not be possible. You need at least 3 carbons to make a ketone. A 3-carbon ketone is called propanone. And notice, if the double bonded oxygen was on the end, we'd call it propanal. In the middle, we call it propanone. This is also known as acetone, and it's the solvent that's used for nail polish remover. Very effective stuff. Butanone would contain 4 carbons. Hexanone would contain 6, but since there's more than one middle carbon you can put it on, you could have 2-hexanone or 3-hexanone. This would also be 3-hexanone, and this would be 2-hexanone. 3 carbons in from the end, 3-hexanone. And those are ketones. They're very good solvents. A carboxyl group. These are the third group of isomers. A carboxyl group is a carbon single bonded to one carbon and double bonded to another. Sorry, oxygen. So you can see here, we have a carbon single bonded to one oxygen, double bonded to another. A carbon single bonded to one oxygen, double bonded to another. And again, it's a primary-secondary thing. If this carboxyl group is on the end of the molecule, primary, it's an organic acid. However, if it's in the middle of the molecule, it's called an ester. And the naming of esters is a little tricky. That's going to take some doing. So organic acids have the carboxyl group on the end. These are weak acids. In other words, they don't ionize 100%. And esters contain a carboxyl group in the middle of the molecule. These are interesting. They're used for natural and artificial flavoring. So organic acids would include methanoic acid, which is what's injected into you when you're bitten by an ant. And that's the result of the fire ant sting. A raised white pustule. Isn't that a great word? Pustule. That lasts for many days. Yeah, 5 minutes is more than enough. Yeah. Ethanoic acid, or acetic acid, is found in vinegar. White vinegar is typically a 5% solution of acetic acid. You can make acetic acid by oxidizing ethanol, which is why wine that's been left to sit far too long that oxidizes starts to taste like vinegar, because it's turned into vinegar. That's where you get white wine vinegar, red wine vinegar, rice wine vinegar, apple cider vinegar. Okay? Balsamic. Oh, so good. Propanoic acid would have 3 carbons. Butanoic acid would have 4 carbons. And in every case, this carboxyl group, the COOH, is on the end of the molecule. And by the way, this H at the end, that's the H that ionizes when you dissolve an organic acid in water. Organic acids, unlike all other organic compounds, are electrolytes. They're weak electrolytes. They'll barely conduct electricity when you dissolve them in water, but they do ionize to a small degree because this H on the end of the carboxyl group can ionize in water. Also, the bigger the molecule is, the weaker it acts as an acid. So methanoic acid is the strongest organic acid. By the way, butyric acid, have you ever seen cheese that's sat out too long and gets like an oily droplets on the top of it? Those oily droplets that exude the stench of rotting cheese, that's butyric acid. It's one of the nastiest smelling compounds there is. By the way, ethyl butyrate, I believe it's ethyl butyrate, when you combine an organic acid, butyric acid, with an alcohol, gives you artificial pineapple flavor. And that's what we're going to look at next. This is ethyl butyrate, an ester. So if you take butyric acid and you react it with ethanol, you get ethyl butyrate, and it no longer smells like stinky cheese. It's now pineapple flavored. Pineapple. Let's look at these esters where these carboxyl groups are in the middle of the molecule. The side that doesn't have oxygen in it, in this case, it's this side right here, will get a YL after its name. So for example, this is a single carbon. This would be methyl. See? Methyl. And the side with oxygen gets the ending anoate. this side has the oxygen. So if we use oxygen to split this molecule in half, the side that doesn't have the oxygen goes first. The side that does have the oxygen goes second in the name. There's 1, 2, 3 carbons in this molecule, so this would be propanoate. So ethyl methanoate is made from ethanol and methanoic acid, is artificial lemon flavored. This is the ethyl part of it, and this is the methanoate part of it. Pentyl ethanoate is artificial banana. It's made from pentanol and ethanoic acid. This is the pentyl part. This is the ethanoate part. So again, the part that has the oxygen, double bonded oxygen, gets the O part of the name. Pentyl, 5 carbons, ethanoate. By the way, this is also known as artificial banana flavor. Pentyl ethanoate is given off by overripe bananas. And then we have 2 functional groups that contain nitrogen. They are amines and amides, and they look identical. They both have NH2. But amides add a double bonded oxygen to that same carbon that the nitrogen is bonded to. So this is an amine group, and this whole thing here is called an amide group. So amines contain an amine group. It can either be primary or secondary. Notice there's a number in front. If the example on table R has a number in front, that means you need to use the number when you name the compound. However, if the example doesn't have a number in front, that means you don't use a number when naming the compound. That should make it easier for you. Amides contain this amide group at the end of the molecule. And we use amines for making amino acids. Amino acids. And those are used for making proteins. And amides are used for making rubber and paper. So let's look at amines first. First, we have methanamine, which is a single carbon with the amine group bonded to it. We have ethanamine, which is 2 carbons with the amine group bonded to it. Propanamine. Now, we call this 1 propanamine because we could also bond this NH2 to this carbon here, in which case it would be called 2 propanamine. 1 butanamine would have the amine group at the end of the molecule. You could also bond the amine group to one of these carbons, in which case it would be called 2 butanamine. The way amino acids work is that all amino acids have an amine group. You notice the NH2? They all have NH2. They all have NH2. That's the amine part of the amino acid. There's also the acid group. Here's the COO, 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 COO. They all have it. So it's a combination of amine and acid. And what differentiates one kind of amino acid from another is the side chain. The structure of the side chain determines what kind of amino acid you have. If you go on to take biochemistry in college, you'll learn about all of these amino acids. Okay, amides. Methanamide would have 1 carbon with the amide group. Ethanamide would have 2 carbons with the amide group. Propanamide would have 3 carbons with the amide group. And butanamide would have 4 carbons with the amide group. On every single case, the amide group, CONH2, is on the end of the molecule, just like in organic acids. Now, isomers. Alcohols and ethers are isomers of each other. The only difference is where the O is positioned. In the alcohol, the oxygen is bonded to one of the bonds that carbon would usually just bond to hydrogen with. Whereas in an ether, the oxygen is stuck between the carbons in the molecule. It's like the difference between having something stuck to the surface of your teeth and something jammed in between your teeth. They both have 3 carbons. They both have 8 hydrogens. They both have 1 oxygen. They are isomers of each other. Aldehydes and ketones are isomers of each other. They both have the double bonded oxygen carbonyl group, but it's just the position that makes the difference. Propanal and propanone both have 3 carbons. They both have 6 hydrogens. They both have 1 oxygen. However, they are arranged differently, which makes them isomers of each other. Organic acids and esters are also isomers. Again, in organic acids, the carboxyl group is on the end of the molecule, and in an ester, it's in the middle of the molecule. They both have 3 carbons, they both have 6 hydrogens, they both have 2 oxygens. They're isomers of each other. Now, let's see how these form. Ethers form through a process called etherification. To make an ether, you react 2 alcohols together in the presence of a dehydrating agent, sulfuric acid. This will form an ether and water. The process is also known as dehydration synthesis, since you're removing water, that's the dehydration part, to make a new molecule, that's the synthesis part. So if we react methanol and ethanol together, I'm drawing them with the functional groups facing each other. The H of one alcohol and the OH of the other alcohol will be removed by the sulfuric acid, which acts as a catalyst. It breaks the bond. So the H and the OH, let me give you that. Sulfuric acid acts as a dehydrating agent, removing H from one alcohol and OH from the other to form water. The 2 broken alcohol molecules will join at the break to form an ether. So we remove an H and an OH to make water, and the 2 broken halves of the molecule will join together to make the ether. The name of the ether is based on the names of the alcohols that made it. If we used methanol and ethanol, the name of the ether is methyl ethyl ether. So very cleverly, the name of the ether is actually the recipe for the ether. To make methyl ethyl ether requires methanol and ethanol. Isn't that clever? Methanol and methanol will make dimethyl ether. Ethanol and butanol will make ethyl butyl ether. And to make methyl propyl ether, we need methanol and propanol. So the name of the ether acts as a recipe to tell us how to make that ether. To make esters, you use esterification. Esterification puts a COO in the middle of the molecule. And the only source you have for COO is organic acids. So you react an organic acid and an alcohol together. This will produce an ester, and then the sulfuric acid catalyst will remove water. Here's the methanoic acid and the ethanol. The sulfuric acid will act once again as a dehydrating agent, removing H from the acid and OH from the alcohol to form water. Then the 2 broken molecules will join at their breakpoints to form an ester. So the dehydrating agent will remove 2 H's and an O, forming broken molecules, and where they're broken, they'll join together to make an ester. The name of the ester is the recipe for the ester. We reacted methanoic acid with ethanol, and this formed ethyl methanoate. So to make this, we need ethanol and methanoic acid. That's where this came from, the methanoic acid. So if we react methanol and methanoic acid, we'll make methyl methanoate. Ethanol and butanoic acid will make ethyl butanoate. And if we want to make pentyl propanoate, we'll need pentanol and propanoic acid. So the name of the ester tells us how to make that ester. Making soap, saponification. We take a molecule of fat, and it is one seriously fat molecule. And what we do is we add to it sodium hydroxide. This will cause each of the three arms to snap off of this fat molecule. The OH from the sodium hydroxide, okay, we'll start with the NAs then, I guess. The NAs from the sodium hydroxide will bond to each of these arms that was once on the fat, and the OHs will bond to the three carbons to form glycerol. And the molecules that are left behind, these sodium salts of fatty acids, that's what soap is. So glycerol is always a byproduct of soap manufacture. Soap is a really interesting molecule because it acts as an emulsifier. Remember, like dissolves like. So grease will not dissolve in water because grease is nonpolar and water is polar. But soap has both a polar end and a nonpolar end. The nonpolar end will dip into the grease, and these polar ends will stick out of the grease, giving water something to grab onto. So soap acts as a go-between between water and grease. It's an emulsifier. Other examples of emulsifiers would include soy lecithin, which is used to hold the oil and water together in mayonnaise. Finally, polymers. Polymers are molecules that are made up of smaller molecules put together. Imagine you have a bridge. Here in the Hudson Valley, we have the walkway over the Hudson. And imagine you have 1,000 people standing next to each other on that bridge. And at the blow of a whistle, all the people link hands together or link arms together to form a long continuous chain. Each individual person would be considered a monomer, and the large molecule that's formed when everyone links their arms would be the polymer, because poly means many, and mer, remember isomer, is another word for molecule. It's a suffix that means molecule. So here are our individual monomers, and then we're just going to join those monomers together by bonding them to form a polymer. We don't actually draw this very large structure. We abbreviate it by putting the monomer in parentheses with the number of monomer units outside the parentheses. Polymers are usually thousands of monomers long. To name a polymer, you just put poly in front of the monomer name. So ethene would make polyethene. This is used for plastic sheeting. The recycling symbol is PE. Styrene makes polystyrene. The recycling symbol is PS, and it's used for making styrofoam. You can also use it to make plastic utensils or model parts. And propylene makes polypropylene. Polypropylene is used for food packaging. So these containers you might put your leftovers into are made of polypropylene. Butadiene makes polybutadiene, which is used for making the rubber in tires. Okay, let's look at a couple of examples of polymers. First, we have addition polymers. Addition polymers form by addition reactions, which involves breaking double bonds to join the monomer units together. So let's say we take chloroethene. Eth is 2 carbons, ene is a double bond, chloro means there's a chlorine bonded to it. Chloroethene also goes by the nickname vinyl chloride. Let's say we break those double bonds. This will give the carbons an extra bond to use to bond to each other. Now, instead of having vinyl chloride, we have polyvinyl chloride, which goes by its abbreviation PVC. We have, in this case, repeating units of this monomer right here, polyvinyl chloride. We use this PVC to make PVC pipes, of course, but vinyl can also be used for shower curtains. Vinyl can also be used for steering wheel covers and dashboards. Vinyl can be used for vinyl siding for your house, and it can also be used to make record albums. Very versatile stuff. Another addition polymer would be tetrafluoroethene. Again, eth is two carbons, ene is double bonded. Tetrafluoro means that there are 4 fluorine atoms on the molecule. Tetrafluoroethene. If we break the double bond, this will free up space for the molecules to join with each other to make polytetrafluoroethene, otherwise known as PTFE. PTFE also goes by the trade name Teflon, and it's what's used to coat the inside of nonstick pans. But be careful, it can actually flake off over time. And it's not exactly non-poisonous once it's flaked off. So be gentle when you're cleaning your nonstick pans. Only use a sponge and never use metal utensils to stir. Use wood utensils when you're stirring. Condensation polymers use dehydration synthesis to join the monomers together. For example, if we react terephthalic acid with ethylene glycol, the H from the acid and the OH from the alcohol will be removed and the two molecules will bond together. But notice that terephthalic acid has 2 acid groups and ethylene glycol has 2 alcohol groups, which means when you remove those H's and OH's, you can form a long chain of these molecules. By the way, when you react an acid with an alcohol, you form what's called an ester. And when you make a polymer out of an ester, you make what's called polyester. Polyethylene terephthalate. Its recycling symbol is PETE, peat. Polyethylene terephthalate. Polyester. By the way, there are naturally occurring polymers like wool and cotton and DNA. Now, there's also polymers that you can stretch and bounce. These are called rubber. Natural rubber is not terribly bouncy. It's not very stretchy, and it's very soft, and it's very tacky. So how do we make it stretchy and bouncy? Well, Charles Goodyear came up with the solution when he accidentally knocked the right amount of sulfur into his rubber. And he found that the resulting product was tough, stretchy, and bouncy. See, the way it works is rubber molecules are all curled up. And if you join them, like a frog joining 2 twigs, with something that forms 2 bonds, like let's say sulfur atoms, if you pull on either side, the molecules will stretch, but the sulfur will cause it to snap back into shape again. This is what makes rubber stretchy and bouncy. The process of adding this sulfur to cross-link with these rubber molecules, this process is known as, I'm about to say it, vulcanization, vulcanization. Woohoo! Ladies and gentlemen, I give you chemistry. Thank you so much for sticking with this throughout the year. It's been a privilege to bring this course to you. When you take your exam, whether it be the Regents or anything else, best of luck to you. And don't forget to check out the music videos. And this is the last time I'm going to say it, guys. Bye.